This video is an introduction to a type of lipids found in natural plants known as essential oils. The basis of these lipids is the use of a 5-carbonsdiene called isoprene. The mixture of hydrocarbons, alcohols, aldehydes, and ketones that have multiplied the number of carbons by 5 each time is known as terpenes. The combination of isoprenes yield 5 carbons plus 5, that will be 10, 15, 20, 25, 30, and even 40. We have seen these kind of molecules in the past. For example, you have done the study of chiral substances, and one example for that is the molecule of menthol that has 3 chiral carbons. I know that you have seen that. We can see also carbon that has, this is cyclic, so this one is just an alcohol, a cyclic alcohol. We also have a ketone, and then we have an open chain, this is geraniol. But the importance of these kind of substances is that from them we can do the synthesis of steroids. Let me show you the molecule of isoprene. So let me just make sure that you guys see the whole page. All right, just in case you need that. And these carbons can combine in different ways. For example, we have that isoprene, the actual name for the molecule of isoprene. It is, this is going to be called the head, and that one will be called the tail of isoprene. Can be considered like joining the two molecules. This is 2-methyl-1,3-butadiene that by combination we can create, for example, alpha-pinene. If we look at it as just a simple combination, we can create 2 different substances with the same number of carbons. If we combine this head and tail, we create a single bond that will be found in bay leaves. It's called myrcene. This is finding oil of bay leaves. But the same 2 units can also combine to form a cyclic structure. Let me show you on the next page how that looks like. But before I show you that, we can have terpenes with even 14 carbons. You guys have seen beta-carotene in other courses. When you did a discussion of UV spectroscopy, most of the time we talk about the color orange of carrots because of the high number of conjugated double bond that moves from the UV to the visible spectroscopy. It has a really high lambda max with the epsilon very high as well. So we know that we have seen this kind of products in the past. So that is for beta-carotene. You also have seen CAM4 because you have in the chapter of cycloalkanes, you have seen how we can have a bridge cycloalkane, and in this case is instead of norbornene we have now a ketone group, and is this, I remember that it was kind of difficult sometimes for the students to do the drawing when I taught this class, but it's very simple to do the drawing. It's like a roof of the house, and then you have your bridge on top, and if we're making CAM4 you have the 2 metal groups, all right, and in this case it's gonna have a ketone group. So that you guys have seen that in the past. Continuing with the discussion, so we say that it can combine in 2 different ways. It can combine to make a cyclic one. I did the drawing twice so you guys can see it, and it can also combine to make an open chain. But what is the importance of this? That after adding 5 carbons each time, we can increase to produce one that is a 15 carbons unit called farnesyl. Those 2 farnesyl units will be phosphorylated and are going to combine to form one that will contain 30 carbons, and that's called squalene. That is the precursor of the synthesis of cholesterol, and cholesterol is of extreme importance for us because it is one of those lipids that is going to be found in the membranes. Excuse me. Now, the next is if it has 2 units of the isoprene, that will be called a monoterpene. That is going to be found in plants. If it has 3 units of the terpene, that's called sesquiterpene. 20, that's a dipertene. And the one that is interesting for us is squalene, is a tripertene, because it will be the precursor for the synthesis of cholesterol. Cholesterol is made from lanosterol. And we are going to look at the mechanism of the synthesis of lanosterol that includes the formation of a carbocation and a cascade of carbocations with hydride shift and methyl shift. A little more. Instead of using the molecule of isoprene per se, you guys, this is isoprene, we're going to use 2 isoprene equivalents because that reaction, as we showed, just joining together is not going to work. But instead, we will be using a phosphorylated unit that can work for an SN2 reaction to eliminate one of the 2 phosphate units and increase in carbons by 5. So instead of doing that, we're going to have to learn how to do the synthesis of these 2 compounds. And for that, the first one we call a dimethyl allyl because you have methyl in an allylic carbon. Dimethyl allyl pyrophosphate and isopentenyl pyrophosphate. So those 2 can be synthesized by what is called the mevalonate pathway, and that is using 3 mevalonate pathway is the use of 3 units of acetyl coenzyme A. They are going to combine using condensation reactions that we have learned in the past, Claisen condensation and an aldol condensation, and then after we have created this is a carboxylic acid with a tertiary alcohol and a primary alcohol, and it contains 6 carbons. But remember that the molecule that we are attempting to make will have 5 carbons, so that it will require the addition of 3 units of ATP, so that is 3 phosphorylation. And after the 3 phosphorylation of this compound, we are going to do a decarboxylation to produce one of these 2.